We're starting with a new unit, that is fuzzy set theory. This is the outline for today's lecture. So first we'll start with a review of conventional sets, and we'll then also look at a few operations which can be performed on conventional sets or classical sets. Then we will introduce fuzzy sets formally. We'll then look at the different notations for representing fuzzy sets. Then certain important terminologies related to fuzzy sets will be discussed, and we'll be looking at a few problems on these concepts. So, the last lecture we already saw one example of conventional sets, right? So quickly, we'll just revise what we discussed last time. So a conventional set is a set with a crisp boundary, a crisp or a fixed boundary, right? So, so we saw a classical set of real numbers greater than 6, right? So it is somewhat like this, right? So if you look at this particular figure, this represents a classical set. So we are trying to model this particular set where the set is going to represent the height of a person, and or the specifically the height of tall people. So so if I mean A is a set of tall people, so on the basis of height, you're going to classify that person as tall or not, right? So if you go for the conventional set or the classical set to represent the same, then if you try to actually visualize it, then this kind of a membership function is formed for a classical set. So what happens is you decide your threshold. So you're saying that beyond 6, so beyond 6, your set is a classical, beyond 6, the element, whichever is there, will be included in the set, right? Whatever is greater than 6, you're going to include it in the set. So on that basis, if you try to plot a graph of the same, what will happen is on the x-axis, the height values, and on the y-axis, you are plotting the membership. Membership meaning whether the element is belonging to the set or not. Given an element, given a value, whether it is belonging to the set or no, then in that case, you notice that after 6, there is a sharp or a steep edge, right? At this point. Okay. So, the moment the value reaches 6, the membership becomes 1, and beyond 6, everything is 1. Right? So if you if you're trying to plot it graphically in terms of membership, so if you look at the membership function, this plot is called the membership function plot. So if you look at the membership of an element in the set, then there is a steep rise, right? There's a sharp rise directly. Okay. So the drawback of this is that a person who is just a
हाँ
bit.
है ना क्या चाहिए देखो फैंटम मैंडल फैंटम मैंडल ब्रो फैंटम है रुइनेशन मैंडल
Hello, Kshitij.
next on
Yes. Okay. So the problem with this kind of a set for this representation is that it will classify a person who is having height slightly greater than 6 as tall, but which is slight, a person who is having a height which is slightly less than tall will not be classified as tall. So that is the problem with this kind of a conventional set to model this scenario. Okay, so it is not always feasible to use a conventional set to model your problems. Okay, and that drawback in fact is removed by what is known as a fuzzy set. Okay, so quickly we'll go through the operations on classical sets. So the operations are union. So you can find out the union of two classical sets. So what is the definition of union? So if there are two classical sets A and B, then you find out the union by combining the elements of A and B, right? So graphically, if you want to represent the same, then it is this shaded portion. The shaded portion is A union B, right? So all the elements of A and all the elements of B taken together is A union B. Next is intersection. So intersection is basically the common region, right? So whatever are the common elements of A and B, that is basically the intersection of A with B, right? So if there are no elements which are common, then of course the what will be the intersection of A and B? And in this case, they are common. There are some common elements, right? But if there are no common elements, so if it is something like this, A is this set, B is this set, right? There's no commonality. So what will be the union? Oh, sorry, what will be the intersection? What will be A intersection B in this case?
Zero. Null set.
Null set, right? Null set. Okay. Next is complement of a classical set. The complement of a classical set is basically the elements, the collection of all those elements which do not belong to that set. Okay. So graphically, it is represented by the shaded region. So considering that X is the universal set, this is X, right? This is X, and A is a subset of it, right? So A is drawn from X basically. A is a set which is constructed from X. So in that case, what is A complement, denoted by A bar notation, is the all the elements in which do not belong to A. Okay, so that is complement of A. Next, next operation that can be performed is difference, set difference or subtraction. So what is difference? Difference is basically if I write A minus B or A difference B. This is the notation, and it simply means that it is the set of all X such that X belongs to A, but X does not belong to B. So X belongs to A, but X does not belong to B. Or this could be one more way in which you can compute difference, A difference B. Again, it is not A difference B is not the same as B difference A, right? What will be B difference A by the same terminology? What will be B difference A? It will be the set of all X such that X belongs to B and X does not belong to A, right? So whenever we are talking about difference, then in that case, it always is with respect to some other set. So uh, your difference of set A with respect to set B, okay, or B with respect to set A. That is as you see here, right? So it is B with respect to A, B minus A. Okay. If you want to look at it graphically, Then the shaded region represents A difference B. Everything that is there inside A but not in B. It should be inside A but not in B. So this part of it, this region, right, is part of A, but it is also part of B. So that has to be removed, right? That is A difference B. Similarly, B difference A, it will be there inside B, but it will not be in A. Okay, if it is in A, then remove it. So B difference A is whatever is there in B apart from what is common between A and B. Right? Remove that. So B difference A is this. Okay. Next, we move on to the properties of classicals. So what are the properties? Some operations are commutative, like union. A union B is the same as B union A. What about intersection? Intersection is also commutative. A intersection B is the same as B intersection A. Next is associativity. What is associativity? The order does not matter if we talk about applying a particular set of operations in sequence, right? So A union B union C. Okay, if you find B union C first, or if you find A union B first, it does not matter. The order does not matter. Okay, you will get the same answers. So this is equivalent to this. What about intersection? The same can be applied with intersection, right? Whether you find B intersection C first, or you find A intersection B first. This is equivalent to this. The left hand side is equivalent to the right hand side. Next is distributivity. What is distributivity? So when you are talking about union and intersection, union is distributive over intersection and intersection is distributive over union, right? So A union of B intersection C then is equivalent to A union B, you distribute it, intersection A union C, right? Similarly, the other way around, you're distributing intersection over this, right? So this is the distributivity property of classical set. Next is idempotency. What do you understand by idempotent operation? What do you understand by an idempotent operation?
Involving only one set.
Okay. So basically,
Idempotency when the order does not matter and the result in the end comes same
result,
is irrespective of the order.
okay. So idempotent operations means if you perform that operation n number of times, the result will remain the same. Okay. So what is that operation? A union of a set with itself will give you the same set. Okay. So A union A is equal to A. Similar for A intersection A is equal to A. Right? Intersection of the set with itself will give the same set. Will not change it. That is idempotent. The concept of idempotency comes in case when you study distributed systems, where you have to be careful about whether the transaction, whatever is executed, that those operations have to be idempotent, so that when there are faults in the system, there is not much loss. Okay, so that is a property of distributed systems, idempotency. Next is transitivity. If A is a subset of B is a subset of C, then A is a subset of C. So when we talk about containership or subset relation, then if you have something like this, then automatically the smallest subset will be a subset of the larger one, C. It's like A is inside its, right? A, B, and C. So A, B, C. Sorry, right? So that is transitivity. Next is identity. So identity. So A union null set is equal to A, and A intersection null set is equal to null set. A union X is equal to X, and A intersection X is equal to A. Okay. So what is X? X is the universal set. X is the universal set. So if you find the union of any of the subset of the universal set with the universal set, then in that case you will get the universal set. If you find the intersection, you will get that set back, right? And if you're talking about the null set, then if you take the union with the null set of any set, then you will get that set back, right? Because null set is not containing any elements. Similarly, intersection, if you take with null set, you will get the null set back. Okay? So next is involution. Involution is double complement. So if you find the complement of A and then again you find the complement of that, then you will get A back, right? Involution. So A is your set. What is A complement? This region, right? And what is this set's complement? It is A back, right? That is involution. Double complement of a set is the set itself. Law of excluded middle. So what is law of excluded middle? A union A complement is the same as the universe of discourse. This is the universe of discourse X. Right? If you take the union of A with A complement, you will get the universe of discourse. Right? And if you take the intersection of A with A's complement, then you will get the null set. Okay. Then De Morgan's laws. What are De Morgan's laws? A intersection B, the whole complement, is equal to A intersection union, A complement union B complement. Okay. Similarly, if you take the complement of A union B, then it will be intersection of the individual complements, right? So these are De Morgan's laws. Now, similar such properties and laws, there are some similar properties which you will be studying as part of fuzzy sets as well. Okay, so it was important to revise this. So we will revisit the properties of fuzzy sets and then we will compare these two. What is the difference? Okay, how are the properties of fuzzy sets different from classical sets? So we'll revisit the same properties for fuzzy sets later on. Okay. So this was just a short summary of classical sets and the properties of them. So with this, let us move on to fuzzy sets. So fuzzy logic was introduced by Lord Fizade in 1965, and the word fuzzy means vagueness. Okay, so basically we have already seen uh, what the use of fuzzy sets was in last in the last lecture. So basically the reasoning, the kind of reasoning that is done using traditional logic, that is all very crisp, it is deterministic, it is precise, and um, everything is very fixed. So it is not very simple for us to use the same to model a the real world scenario. So you cannot go for that classical set every time. So you need a different kind of a model to represent the real world scenario, and that is the fuzzy set. Okay. So the knowledge that you're going to deal with in the real world is, it is vague, it is imprecise, it is uncertain, it is ambiguous, it is inexact, it is probabilistic in nature. So that kind of representation you require a fuzzy set. Okay. Your crisp, your classical sets, they are crisp in nature, they are fixed, they have a fixed boundary, right? So they are unable to cope with such unreliable and incomplete information. So that is why fuzzy set theory was introduced by Professor Lord Fizade for dealing with such incomplete and vague information. Okay. So let us look at the definition of a fuzzy set. Okay. So this is the formal definition of a fuzzy set. If X is a collection of objects which is denoted generally by X, then a fuzzy set A tilde, so this is the notation which is used, A tilde, A with a tilde on top. Okay. In X is defined as a set of ordered pairs. Okay. X comma mu A of X. Okay. This is X comma mu A of X such that X belongs to capital X. Small x belongs to capital X. So basically X, when you're talking about this capital X is a collection of objects. Okay. And generally they are denoted by small x values. Okay. Then a fuzzy set A tilde in X. A tilde, that fuzzy set is, it is defined in X within the context of X, this capital X. X is basically your universe. Okay. And it is defined in such a way uh, that it is a set of ordered pairs. Okay. So you have for each X, there is one value which is paired along with it, and that value is called as a membership value. Okay. So X has a mu A of X. So the mu is a function basically. It's called as a membership function. Okay. Mu A of X is called as a membership function, or MF for short, for the fuzzy set A. Okay. So the MF, or the membership function, maps each element of X to a grade, to a membership grade or a membership value between 0 and 1. Okay. So the moment I say that this MF is directly mapping the value to either 0 or 1, then I say that my set is a classical set. Okay. And the moment I start giving grades between 0 and 1, my set becomes fuzzy set. Okay. So for example, if you consider that the set of tall people only, so if I use this fuzzy set, so suppose I have, if I use a classical set notation, then what do? I say, okay, 5 5.999 was not tall, right? So I give the membership value 0. Okay. Then I say 6. Okay, I start from 6. So I say 6 is 1. 6 is membership value. It is belonging to the set. Then I say 6.1 also is 1. 6.2 is 1. Okay, and so on. Everything below 6, so it is 5.5, is having membership value 0. 5.6 having membership value 0, and so on. Right? Everything below 6 is having membership value 0. But everything above 6 and above is having membership value 1. So what is this? This is having membership value 0. All this is having membership value 0. That means it is not part of the set A. Only 6, 6.1, 6.2, all these elements, these are part of set A. So this, whatever we have written, is a classical set. So the moment I say that my membership function is directly going to map the value to either 0 or 1, then that set becomes a classical set. Only if I'm giving a gradation of values from 0 to 1, in between 0 to 1. So I start giving the values, at an earlier point. So I say, okay, let me assume that uh, 5 point, 5 beyond. I start giving my membership values from 5 beyond 5. So I say beyond 5, I'm starting, okay, I say 5 is like 0. 5 is not having some membership, but 5.1 is having some membership like 0.2. Okay, it is somewhat tall. 5.1 is somewhat tall. Okay. And then I keep on increasing the values gradually. So I say 5 is 0, 5.1 is 0.2, 5.3 is 0.5, and so on. I keep on increasing. And then from 6 onwards, I make it 1. So 6 is 1, 6.1 is 1, and so on. Okay. Keep on giving the values. So this way of representing the set is a fuzzy set. So this is a fuzzy set that I've written. So whatever I've written here is a fuzzy set. Okay, because I'm giving membership values between 0 and 1 to the elements. Okay, and beyond. Okay, so if I want to represent this graphically, so it will be something like this, the plot. You remember the plot which I had drawn earlier for that tall person was a sharp edge like this, 90 degree, right? Something like this. At 6, it became 1 and so on, right? 6, this is 6. If I want to represent this on the graph, how will it look like now? So here somewhere there is 5, right? This is 5. So beyond 5 started giving the membership values. So it becomes a straight line, sloping line like this with an increasing slope, right? And at this point, it becomes 1, right? So if I want to represent the same thing graphically, this membership function graphically, I am representing it. It looks like this. So this is the height, x. This is the membership, mu. Membership function, mu. And this is my fuzzy set. Okay. X is called as the universe of discourse or the universe, right? The universe may consist of discrete objects or it may consist of continuous values. So in this case, it is discrete or continuous. In the case of height, the universe is discrete or continuous.
Continuous.
It is continuous, right? Height is a real value, right? It will be continuous. So let us look at the types of universe of discourse. Okay? So fuzzy sets, the first type of universe of discourse is discrete, non-ordered. The universe is discrete, non-ordered. Okay. So let us take an example. So X, the universe of discourse, is the set of these cities: Mumbai, Bangalore, Kolkata. Okay. So in this case, the kind of values that are there in X, these are actually They are discrete values, they're distinct values, right? And they are not having any kind of ordering as such. I can write Mumbai first, or I can write Bangalore first, or I can write Kolkata first. Non-ordered. These are just a collection of objects. Ordering is not important here, actually. Okay. So I need to find the fuzzy set desirable city to live in. Okay. So all of you try to write this down as a fuzzy set. So let me say my fuzzy set is desirable city to live in. Let me call it C. C tilde, right? So how will I write it? Use the same notation that we used earlier. You remember? It is ordered pairs. You have to write it in the form of ordered pairs. So you say into curly brackets the element and the value. The element and the value. But what value? The membership value. Okay. So element is, in this case, Mumbai is the element. You have to decide the value. Okay. Put a comma. Next element, Bangalore, put the value. And then you say Kolkata and you put the value. Now, when you're putting the values here, remember that when you design such a set, it will be very subjective in nature, right? It's going to be very subjective in nature. So what do you understand by that? For you, Mumbai might be a desirable city to live in. For someone else, Mumbai might not be that desirable city. It is all on perception, right? Okay. So you might say, X person might say that Mumbai is the best, Bangalore is okay, Kolkata is not, is fair enough. Okay. So I just give it a degree, something like this. Okay. So desirable city to live in could mean different things for different people. So always understand that when you're modeling a fuzzy set, the way you model it could be very subjective. Okay. But when you model it very subjectively, it's not going to make sense every time, because when you model use these fuzzy sets for actually solving a real world problem, then you need to know what is the end result, what is the goal that you want to achieve. Okay. Whether you want to actually, do you have a certain set of parameters available with you which actually tell you whether this desirable city to live in will be, I mean, Mumbai will be good, or Bangalore will be good, or whatever. Okay. So very important when you're actually modeling all these systems is some knowledge. That is the knowledge of the domain. The domain knowledge plays a very, very important role while designing such systems. Okay. So it is not necessary that you will, I mean, now for example solving, it is okay. Now you can have, I can expect the different answers from you, right? But when you are modeling it with respect to some application, then you have to consider what is intuitively correct, what is logically correct, and some assumptions. If there are some assumptions, you have to write down those assumptions. And in the real world, when it is modeled, then the domain knowledge comes into picture. The domain experts are consulted. Then only you can model the systems. Without the intervention of domain experts, you cannot model such a system. Okay. So this example is an example of a discrete non-ordered universe. Okay. So everyone will get different answers. Okay. Someone could give Mumbai 1 also. It depends. You love Mumbai, na? Amchi Mumbai. Yes. So I love Mumbai. So that is perception. So it is fine. All answers are correct. Uh, Next is Next type of universe of discourse. Okay. Next type of universe is basically discrete and ordered. Discrete, ordered. Let us take this example. So x is equal to 0, 1, 2, 3, 4, 5, 6. It is basically the set of number of children a family may choose to have. So universe of discourse is given to you. It is x. X is the uh, number of children a family may choose to have. So it could be 0. A family may choose to have 1, 2, 3, 4, 5, 6. 6 is the max possible which is given. Okay. Now this particular universe is discrete and it is ordered. Ordered in the sense that the numbers, the elements which are there, they are ordinals, right? Okay. So while writing it in this notation, actually, when I write it in this notation, which notation? The ordered pairs notation. So I have used one ordered pairs notation in the beginning, right? We have used that, comma separated. So element, comma, membership value. Element, comma, membership value, comma separated, right? So when you're writing in this ordered notation, it is fine. But if you're plotting it, if you're trying to plot it, then you have the order will matter. So in the previous example, if I plot it like this, if I try to plot it as a graph, it was Mumbai, Kolkata and Bangalore. So if I write MKB or MBK and put all the values something like this or whatever, okay, this is a, this is the plot, right? In the previous case, if I write MKB or KBM or whatever, order does not matter, right? But when I'm trying to plot this, what will happen? Order will matter, because this x actually will be an integer scale, right? X will be integers. It will be 0, 1. So this is a discrete and ordered universe. Are you getting it? The difference? Discrete, unordered, discrete, ordered.
Yes, ma'am.
Okay. So let us come back to this example. So you have to represent the fuzzy set, sensible number of children in the family. So how will you represent this? It is subjective. So if I say my fuzzy set is S, you will decide, you will say, okay, some of you will say, okay, it is sensible to have 2 children in the family. Some of you will say it is sensible to have 3. Some of you may say it is sensible to have no children in the family, right? Subjective. But the way to write it is the same. So I let me assume that it is sensible to have 2 children. So what I can do is, to 0, maybe I'm not giving some membership. Okay, so 0 is having membership 0. But 1, I'll give some membership. Okay, maybe I make it as it, since it's close to 2, right? It's not, remember, it's a fuzzy set. It is not a classical set. In fuzz, if it's a classical set, then you may have only 2 or 2 comma 3, something like this, right? But here you have to think of in terms of gradation of membership values. Okay, so you are going from 0 to 1. Okay, one child. One child is fine. So I say 0.4. Then from 1 to 2, I say I increase the membership. So maybe it is not that advantageous. So I say it's 0.8. And maybe 0.8 is the highest value that I want to give. Okay. Like in the last example also, 0.9 was the highest value that I wanted to give. I didn't say 1 because maybe there are some drawbacks which I have to take into consideration. So it cannot be like Mumbai is the best, right? So there are some drawbacks also. So similarly here also 0.8 is the maximum value I want to give. Possible. Then I say 3. 3 I reduce it. Okay, or maybe this is 0.6. This is 0.8. This is 0.4. And 4 is 0.1. And then 5 and 6 I have membership as 0. Fine. So if the membership value is 0, then you need not write them here. You need not write them. It's fine. So the set will comprise of this, and this. It is understood through the universe of discourse that these elements are there, but they are not part of this. I mean, they are having a membership 0 here. So if you plot here now on the graph, you will be able to see what exactly you have done. 3, 4, 5, 6. So you will have somewhere at 2, you will have 0.8. Right? This is 0.8. 1, you are having 0.6. This is 0.8. 3, you are having 0.4 somewhere. Okay. 0.4, 0.1. Fine. And here there are no points. That means these are the only 4 points which are there. Okay. Others are having membership 0. Okay. So this is how you model this particular fuzzy set. It will be different from person to person. So all students, you will have some different perception. The membership value also might be different. Instead of 0.8, you might have given 0.9 or 1. It will be different. It is up to you. Next is the universe is continuous. The universe is continuous in nature. That example we have already seen. That is tall people, right? Let us take one more example. So x is a real number, is a set of all the possible ages for human beings. So real numbers means it is continuous in nature. You have to find the fuzzy set about 50 years old. About 50 years old. I want to form a fuzzy set about 50 years old. How will I form this fuzzy set? Can anyone tell me? When a person is 49, he is about 50 years. 50, right? As you're moving away from 50. So 50 is when you're saying a person is 30 years old.
मैम शायद वो ऐसा ट्राइंगल आएगा जिसमें पीक 50 के ऊपर है.
So it will be, so if you're saying 50, right? on either side. As you're moving to the left of 50, the membership, you're starting model 50 using trapezoidal also. If you're talking about straight lines, okay, you can model this about 50 using this curve also. This is a bell-shaped curve. But remember, for this example, for about 50 years old.
मैम आपका आवाज नहीं आ रहा है, थोड़ी थोड़ी देर में कट जा रहा है.
Hello?
हाँ अभी आ रहा है बट बीच में बहुत कटा जब आप ये ग्राफ्स बना रहे थे.
Okay. Hello? Yeah. So can you model this using above 50, this the right graphs, this graph and this graph? Hello?
Yes, ma'am.
When I say about 50 years old, it should also logically make sense in this case. In this case, it should make logically sense. It should make sense logically. Okay. It can be this. This is correct. This is correct. This is correct. But these two are not correct. These two are not correct in this sense. Are you getting the crux of it? Because look at the statement. The statement is about 50 years old. Okay. There could be variations. That is what I'm saying. There could be variations, but it has to be logically correct as well. If there is something like this, then it has to be logically correct. Okay. So when you're actually designing controller problems or when you're designing a fuzzy inference system, at that time you have to be, whatever you're going to model, whatever fuzzy sets you're going to model, those have to be intuitively correct, logically correct. There could be variations in terms of the ranges of values, like where you're making this peak, where you're starting the membership as zero point 0.8 or 0.9. That this function, the slope of this line could be different. The type of membership function could change. It could change from a bell-shaped curve to a triangular curve to a trapezoid. It could change, but logically it should make sense. That is the crux of it. Okay. So I'll stop at this point for today's lecture, and then we'll continue with this discussion next lecture on.